Hey everyone, and welcome back to Study with Pröf Düdü. Today we are going to tackle a super powerful tool that honestly is like a secret weapon for chemists when they run into some really tricky problems.
So I want you to think about this for a second. How in the world do you measure the heat of a reaction that's, I don't know, maybe it takes 1,000 years to complete? Or one that's super dangerous and might, blow up the lab? Or maybe it's a reaction that's literally impossible to do in a single step. How do you get that energy value? Well, that's where this awesome shortcut comes into play. It's a really clever idea called Hess'S Law. Okay, before we really jump in, you know the drill. If you find these lessons helpful, do me a huge favor and hit that like button and subscribe to Study with Pröf Düdü. It seriously helps the channel grow. Oh, and make sure you click that little bell icon so you never miss out when a new lesson drops.
All right, so here's the game plan for today. First up, we're going to figure out what in the world Hess's Law even is. Then, I've got a great analogy that's going to make it all click. After that, we're going to roll up our sleeves and solve a problem together step by step, and to finish things off, we'll do a quick recap and give you a chance to practice. Sound good? Let's do this.
Okay, Section 1. Let's get right into the heart of it. So what is Hess's Law? So the official definition is the law of constant heat summation, which sounds kind of fancy, but all it really means is this. The total heat change for a reaction, the enthalpy change, is always the same. It doesn't matter if the reaction happens in one big leap or if you take a bunch of tiny little steps to get there. The total energy change from your starting point to your ending point, it's going to be identical every single time.
So you might be asking, why? Why does this work? And the reason is actually pretty cool. It's because enthalpy, which we show with that little delta H symbol, is something called a state function. Now don't let the name scare you. A state function is just a property that only cares about where you start and where you end. It's completely blind to the journey, the path you took to get from A to B. All that matters is the beginning and the end.
This picture right here shows it perfectly. Look, we can take the direct path, and that has an energy change we'll call delta H1. Or we could take the scenic route, the indirect path, where we go through a middle step. The energy for that path is delta H2 plus delta H3. And what Hess's Law tells us, which is so cool, is that delta H1 is exactly equal to delta H2 plus delta H3. The path doesn't matter.
Okay, I know that state function thing can still sound a little academic, a little weird. But don't you worry, I've got the perfect analogy that's going to make this whole idea super intuitive. I want you to imagine you're standing on the first floor of a building. Your goal? Get to the third floor. That's it. Super simple, right? So you've got choices. Path number 1, you could huff and puff your way up the stairs 2 full flights. Path number 2, you could just hop in the elevator and ride up 2 floors. Now, think about it. The distance you traveled is totally different, right? One path involves a lot more walking. But what's the one thing that is exactly the same for both paths? Your change in elevation. Either way, you ended up 2 floors higher than where you started. And that right there is the whole point. Enthalpy is just like that elevation. It's a state function. It only cares about your start point, your reactants, and your finish point, your products. The crazy chemical route you take to get there doesn't matter one bit for the overall energy change.
All right, theory's great, but let's see this thing in action. It's time to actually solve a problem. This is the I do part, so just watch and follow along as I walk you through how to tackle one of these. Okay, here is our target equation. We want to find the delta H for this reaction up top. And yeah, this is one of those reactions that's a real pain to measure in a lab. But lucky for us, we've been given these 3 other equations. We know their delta H values, so our job is to basically treat these 3 equations like Lego bricks, and we're going to rearrange them and stick them together to build our target equation. So here's the 3-step plan. Step 1, we're going to look at our target and find each piece in our given equations. Step 2, we're going to start manipulating those given equations, flipping them around, multiplying them to make them match our target. And step 3, this is the golden rule, you guys. Whatever you do to the equation, you have to do the exact same thing to its delta H. Can't forget that part. Let's start with our first reactant, CS2. In our target, we need one of them on the left, the reactant side. Okay, now let's hunt for it in our given equations. 1, 2, there it is, in equation 3. But, it's on the product side, on the right. No problem. To fix that, we just take the entire equation and we reverse it. We flip it completely. And when you reverse the equation, you have to reverse the sign of its delta H. So that positive 87.9, it becomes a negative 87.9. Easy. Okay, next on the list, SO2. In our target, we need 2 of them on the product side. Let's look. Okay, equation 2 has SO2 on the product side. That's good. But we only have 1 of them. We need 2. So what do? We just multiply that entire equation by 2. And of course, whatever you do to the equation, you do to the delta H. So we also have to multiply that negative 296.8 by 2.
All right, let's take stock. Equation 1, we didn't have to touch it. It's perfect as is. We've got a reversed equation 3, and we've got our doubled equation 2. Now for the fun part. We just add them all up. And look what happens. See how we have a solid carbon on the left and 1 on the right? And 2 solid sulfurs on the left and 2 on the right? These are called intermediates. They're like temporary workers. They show up for a bit but aren't in the final product. So, just like in math class, if something's on both sides, we can just cancel them out.
And once the dust settles, look what we're left with. It's our target equation, perfectly built from our pieces. So the last thing to do is add up all our modified delta H values. We've got the negative 393.5 from the first one, we add the, negative 593.6 from our second one, and we add the negative 87.9 from our third one. Punch that all into the calculator, and we get our final answer, negative 1175 kilojoules per mole. And boom, we did it. We solved for the energy of a reaction without ever having to run it. That is the magic of Hess's Law.
Awesome job hanging in there with me. Now that you've seen one worked all the way through, let's do a super quick recap of the rules, and then it's going to be your turn to try.
Okay, so here are the rules of the game, nice and simple. 1. Know what your target is. 2. Start flipping and multiplying the given equations to build that target. 3. If you flip an equation, you have to flip the sign of delta H. 4. If you multiply an equation by a number, you multiply delta H by that same number. And 5. Add it all up. That's it. It's really just a puzzle, and these are your instructions.
Okay, your turn. Time to put your skills to the test. What you see on the screen is the exact same problem we just did together. I want you to hit pause, grab a piece of paper, and see if you can work through the steps all by yourself and get to that same final answer. Go on, pause the video now and give it a shot. Fantastic job today, seriously. You now have the hang of Hess's Law. And remember, it's more than just a formula you memorize for a test. It's a really powerful way to think about energy, a shortcut that lets us figure out the enthalpy for pretty much any reaction, all by playing with other reactions. And it all boils down to that one big idea we started with. Enthalpy is a state function. Hey, if this lesson cleared things up for you, it would mean a lot if you tap that like button. And if you haven't already, subscribe to Study with Pröf Düdü so you don't miss out on more chemistry lessons. You know, sharing this with a friend from class who might be struggling is also one of the best ways to support the channel. All right, that's all for today. Thanks so much for studying with me. Keep practicing, always stay curious, and just remember, every single problem is just a puzzle that's waiting for you to solve it. You've totally got this. I'll see you in the next one.